All right. So that's sort of the catabolic side of metabolism, right? Like that's the complex, taking something simple and breaking it down into something, taking something complex and breaking it down into simple. That's a catabolic reaction. It's catabolism, right? Now, all of that was a metabolic process for sure. But now that we got like an individual little glucose molecule, if we get it into our bloodstream and it makes its way over to one of our cells, and our cell uses that glucose to keep itself alive, spit out a little bit of energy to pay for all the stuff that it needs to do, um, and spits out some waste products, that is also part of your metabolism. In fact, if you take that glucose molecule and you link it together with another glucose molecule, well, now you took something very, big, broke it down into something small, got it into the bloodstream, and then built it back into something big again. That is a catabolic reaction at first that becomes an anabolic reaction later. And that's what we kind of need to understand about metabolism. It really only goes in two directions, right? You're either breaking stuff down or you're building stuff up. And that's sort of what maintains all of our metabolic processes, right? So we're constantly breaking stuff down catabolically to fuel our ability to build stuff up anabolically, right? So like picture like a chicken breast. You take a chicken breast, you break it down with your stomach acid into amino acids. Those amino acids get into your bloodstream. And then you went for a hike yesterday and your calves are kind of sore. Well, the reason they're sore is because you created like little bits of microscopic damage in your calves. So that damage needs to be repaired. So then, we take that those amino acids and we use it to repair our calf muscles. So I got a little bit of a video to kind of break down. It's not necessarily directly about uh, catabolic versus anabolic, but it is about muscle building, which I think works pretty well when we're talking about like understanding our metabolism. And what's great about this is I will definitely be referencing this video. I will definitely be referencing this video in our exercise psychology class, actually, because this has my all-time absolute #1 favorite quote at the end of this video, and I think it is super motivational. So this video is going to kind of break down a little bit about like why our muscles grow. And that's very much an anabolic process, right? But you will see like the way we do it is we have to create a little bit of like damage first. That's a catabolic process. So you'll always hear like catabolism fuels anabolism, right? That's a classic sort of phrase that we use in biology all the time. But make sure I'm sharing this and then YouTube with the mute thing. There we go. All right, here we go.
Muscles. We have over 600 of them. They make up between 1/3 and 1/2 of our body weight. And along with connective tissue, they bind us together, hold us up, and help us move. And whether or not bodybuilding is your hobby, muscles need your constant attention because the way you treat them on a daily basis determines whether they will wither or grow. Say you're standing in front of a door, ready to pull it open. Your brain and muscles are perfectly poised to help you achieve this goal. First, your brain sends a signal to motor neurons inside your arm. When they receive this message, they fire, causing muscles to contract and relax, which pull on the bones in your arm and generate the needed movement. The bigger the challenge becomes, the bigger the brain's signal grows, and the more motor units it rallies to help you achieve your task. But what if the door is made of solid iron? At this point, your arm muscles alone won't be able to generate enough tension to pull it open, so your brain appeals to other muscles for help. You plant your feet, tighten your belly, and tense your back, generating enough force to yank it open. Your nervous system has just leveraged the resources you already have, other muscles, to meet the demand. While all this is happening, your muscle fibers undergo another kind of cellular change. As you expose them to stress, they experience microscopic damage, which in this context is a good thing. In response, the injured cells release inflammatory molecules called cytokines that activate the immune system to repair the injury. This is when the muscle-building magic happens. The greater the damage to the muscle tissue, the more your body will need to repair itself. The resulting cycle of damage and repair eventually makes muscles bigger and stronger as they adapt to progressively greater demands. Since our bodies have already adapted to most everyday activities, those generally don't produce enough stress to stimulate new muscle growth. So to build new muscle, a process called hypertrophy, our cells need to be exposed to higher workloads than they are used to. In fact, if you don't continuously expose your muscles to some resistance, they will shrink, a process known as muscular atrophy. In contrast, exposing the muscle to a high degree of tension, especially while the muscle is lengthening, also called an eccentric contraction, generates effective conditions for new growth. However, muscles rely on more than just activity to grow. Without proper nutrition, hormones, and rest, your body would never be able to repair damaged muscle fibers. Protein in our diet preserves muscle mass by providing the building blocks for new tissue in the form of amino acids. Adequate protein intake, along with naturally occurring hormones like insulin-like growth factor and testosterone, help shift the body into a state where tissue is repaired and grown. This vital repair process mainly occurs when we're resting, especially at night while sleeping. Gender and age affect this repair mechanism, which is why young men with more testosterone have a leg up in the muscle-building game. Genetic factors also play a role in one's ability to grow muscle. Some people have more robust immune reactions to muscle damage and are better able to repair and replace damaged muscle fibers, increasing their muscle-building potential. The body responds to the demands you place on it. If you tear your muscles up, eat right, rest, and repeat, you'll create the conditions to make your muscles as big and strong as possible. It is with muscles as it is with life. Meaningful growth requires challenge and stress.
As my favorite quote, by the way. Like, I'm gonna get that tattooed, you know? It is with muscles as it is with life. Meaningful growth comes through challenge and stress. So that's kind of talking a little bit about like metabolism, right? Like anabolism and catabolism. So anabolic reactions are where we are building something up, right? We're taking something that's very simple and building it into something complex. Something simple is like an amino acid, right? That amino acid gets shaped together with a bunch of other amino acids, and now we've got a big old complex, protein. We've got carbohydrates. If we took in carbohydrates and then we wanted to store it as glycogen, we would take in, a piece of bread, catabolically break it down into individual glucose molecules, and then eventually build that back up into glycogen inside of our body. And that way we have stored carbohydrates. We can release that glycogen back into our bloodstream to fuel our metabolic processes again. So there's definitely a lot going on. Metabolism is extremely complex, but the big things that we need to kind of have a good understanding on are how we're producing energy with these molecules. And if we can understand that, it will allow us to understand like how to fuel physical activity during exercise, right? So metabolism, like I said, it's any and all chemical reactions. Catabolic reactions or catabolism is the breaking down of complex substances into their simpler compounds. So like carbohydrates into monosaccharides, those are single glucose molecules, right? Anabolic reactions, anabolism, that's taking simpler compounds and building them up into polysaccharides, right? So like glycogen, which is a complex carb, is a polysaccharide. Sorry, we lost Alyssa. Trying to get her back in here. So that is the anabolic reactions, right? And then one of the biggest things that we're going to talk about is general, we call it cellular respiration. Now, a lot of you guys have seen this a lot before. For those of you who are new, cellular respiration can be a little complicated because it is sometimes like hard to visualize. But what we're talking about when we talked about respiration the other day, right? We talked about bringing oxygen molecules into the body so we can use them. Well, cellular respiration is exactly the same thing, except it's your cells doing it, right? So cellular respiration describes how your cells take in nutrients like glucose and oxygen and use it to produce ATP. So ATP or adenosine triphosphate is this really high energy molecule that has like a lot of energy trapped in between its bonds, right? So ATP looks something kind of like this. I'm going to go ahead and open this up here, copy that and take it over here. So here's like a very simple molecule of ATP, right? And so what this is this is a molecule of adenosine, which is actually this right here. It's adenine attached to a sugar called ribose, right? And so that's the sort of adenosine part, right? It's all of this coming together. And then triphosphate are three little phosphates, right? That's what we're seeing there. So those three phosphates coming together is the triphosphate part. So here's the thing. These little phosphates right here, these little like balls that are on the end, there is a ton of energy trapped right here. In between each of these bonds, there is actually a lot of energy. There's actually even a little bit right here, believe it or not, although not very much. Most of the energy is trapped right here in this bond between the second and the third phosphate, okay? So what we want to do is we want to create this ATP molecule. Now, once we have it, what we can do is we can actually break that third phosphate off. We can take this and we can go and shoot it off like that. And if we do that, that is going to release a ton of energy, right? Like a whole bunch of energy is going to get released when we break that third phosphate off. So our body can't store energy directly. If it did, it would just sort of like, you know, flash around and kind of go everywhere. In fact, honestly, that's kind of what you're seeing when you look at like a flame, you know, like when you look at like fire, all that is like electrons just moving around. That's a crazy amount of energy being released randomly. Some of it's heat, some of it's light, you know, there's just a lot of energy kind of getting released when you set something on fire, right? We don't want that to happen, right? We do not want that to happen inside of our body. Inside of our body, we want to have sort of a controlled release of energy. So because we can't store energy directly, what we store instead are ATP molecules. And even then, we can't store very much ATP. So instead of storing that, what we store is the stuff that makes ATP. And that's our glucose and that's our oxygen. So we can hold on to glucose and oxygen. We can spit out ATP, and then we can use ATP to pay for all the energy for all the stuff that we do in our body. So once we break off this third phosphate, what we're left with is ADP, right? And that would be basically be like all of this. This is adenosine diphosphate now because there's two phosphates instead of three. And so what we're going to need to do to be able to like release more energy, we could either break this one down and we could knock this phosphate off. And that'll release a little bit. We'll be left with AMP or adenosine monophosphate, or more than likely, we'll just try to reattach it. And if we can do that, then we can break its bond again. So that's where all the energy is. The energy is trapped right here between the second and the third phosphate there. When we kick this off, it releases tons and tons and tons of energy. So that's what we're talking about when we're talking about cellular respiration. We are describing how our body generates ATP from glucose and oxygen, right? So how the body cells take in nutrients and use it to produce energy. So glucose and oxygen go in, and carbon dioxide, which is a byproduct, and ATP, which is sort of the product here, come out. And that's how I like to think about it. I like to think of it as like a factory, you know, like you think about like how a factory or a business runs. If you're trying to like make something, right? Well, you have like ingredients that go in, you have byproducts that come out. Let's say I run like a scrambled egg business, right? Well, I go buy scrambled eggs, and then I crack those eggs open, and then cook them up on like some type of frying pan, put on a plate, send them out, right? That's my product. But I'm left with like egg shells and egg cartons and things like that. Those are my byproducts. I got to get rid of that stuff, or it's just going to pile up in the back. So that is sort of the product coming in and a byproduct going out. But what's really cool about your body is that it is really good at recycling its own byproducts. So for instance, when you're done with like a little bit of this sort of like production stuff, you get this like, this leftover eggshells, you get these leftover egg cartons. If you had somebody who was like, oh, you know what, I actually run a eggshell art business, and they're like, tell you what, I will take those eggshells and I will use them to make something else, right? So then you take your waste product and give it to this other person, and they use it to make some type of really cool looking art. They are sort of running their the product. The ingredients for their product are your byproducts. And that's another way that your metabolism works, actually. So we have a couple metabolic processes here. We have the anaerobic metabolism, which is pretty simple. Glucose goes in, ATP comes out. We also get a little bit of this byproduct, which is lactic acid, right? Then we have aerobic metabolism, which takes that byproduct of lactic acid, uses a little bit of oxygen, and makes even more energy. So we're getting a little bit lost in the analogies here. Let's go ahead and take a look at what I mean. So like I said, we've got two major forms of energy production. You are going to have the aerobic and anaerobic processes, right? So we're going to look at anaerobic respiration first. Now, if we look at an animal cell, just your classic sort of biology cell here. I'm just going to take that one, because this one I always use. Well, actually, let me see if I can get it without the I want like a really basic one without all the stuff. There we go. Haha. Move that down here. And okay, so here's the molecule that we're creating, right? We're creating a whole bunch of ATP. We'll come back to this in just a moment. Let's put this over here. But here's our little classic like animal cell, right? So I'm going to label a couple of these things here real quick. So this right here, that's our mitochondria, right? Classic biology. It's the powerhouse of the cell. I know. I hate to say it, but there is also just this kind of empty space here, but it's not actually empty, right? This is our cytoplasm, right? So the cytoplasm is the fluid found within our cells. Now, each of these little areas are actually really important. The cytoplasm is not just empty space that doesn't do anything. Not only does it supply like a suspension of nutrients and things like that, that's why we call it plasm. And the fluid itself is just called cytosol, but the cytoplasm is like that fluid when it has like electrolytes and nutrients and like all this other stuff in it. Well, the cytoplasm is the site for, this is where anaerobic energy production takes place. This is where we are actually doing the anaerobic metabolism. So this is one of the places where we produce energy. I did not make this big enough. There we go. Lucky. So that's anaerobic, right? And anaerobic means without oxygen, which is pretty easy to remember if you look at like this and go, oh, okay, yeah, that's happening in the fluid. I can't breathe underwater, right? Like that's the very fluid-based place. And then we have our mitochondria. This is our aerobic energy production. That's where the actual like oxygen side of things comes in. And like you can think of your mitochondria as like, they're almost like a little air pocket, right? They've got a little bit of oxygen delivery coming to this little guy right here, right? So now we've got our two places where we're going to do our production, right? We've got anaerobic respiration. This is ATP that does not require oxygen. This process is called glycolysis, okay? So glycolysis takes place, God dang, I'm getting my tabs all messed up. Glycolysis takes place here in the cytoplasm, right? So if we're looking at like glycolysis as a process, right? We can think of it this way, right? Glycolysis is going to use glucose as a product, right? Or as an ingredient, right? So we'll go glycolysis, we'll go ingredients. Our ingredient here is really just going to be glucose. That's it, right? Little single monosaccharide, one sugar molecule glucose, right? And then the product, you know, what we're making, right? If we look at it, we are yielding 2 ATP, right? We're yielding 2 ATP every time. So we get 2 ATP molecules. And then we have a byproduct, right? The byproduct is something else that we kind of made by mistake. You know, it's the leftover, right? And these are going to be what are called, this is going to be what's called pyruvic acid or pyruvates, right? And so pyruvic acid is really cool. This is actually a precursor to something that you're probably very familiar with, which is known as lactic acid, right? So lactic acid is what we get after we create pyruvic acid. And we'll get to that in just a second. So that's pretty cool, right? This is a pretty good deal so far, right? 1 molecule of glucose becomes 2 molecules of ATP. Now, the one thing that they're not telling you here, and this is what's kind of funny about this, it's actually, for the record, making, and this is, you guys don't have to have this memorized right now, but like, it's actually making 4 molecules of ATP. But it takes 2 molecules of ATP to get this whole process started, which is what's kind of funny about it, right? Like it takes, it's like, you know, in order to make a little bit of money, you have to spend a little bit of money, you know? So you spend 2 molecules of ATP to make 4, you're yielding, you're netting 2 molecules, right? But you're also making a whole bunch of that pyruvic acid. So okay, so this all took place in an anaerobic place, right? This all took place in the fluid of our cells. Now, here's what's really cool about this that we're not spending a ton of time talking about in today's lesson. But what's really cool about this is that it happens super fast, right? Like I'm just like two, right? I'm spitting out 2 molecules of ATP crazy fast, right? So this actually makes a ton of energy very rapidly. But remember, we're making that pyruvic acid as a byproduct every time we do it. So now, like lactic acid, well, pyruvic acid is starting to build up. And so that is going to be in this fluid of our cells, right? So this is in the cytoplasm. So when there's no oxygen present because it's a fluid, right? What ends up happening to that pyruvic acid is it starts to ferment, right? Did anybody in here, and I think I've asked this before and usually the answer is no, but let me ask, did anybody in here get into the bread making craze, you know, when COVID first broke out? Like, I remember like going to grocery stores and there was just like no flour on the shelves because everybody was like, going into like, they're like, I'm gonna learn how to make sourdough bread, you know? Like, has anybody ever done that? Anyone here know how to make sourdough bread? I promise this is related to what we're talking about. Simon?
No, I only learned macaroni and cheese.
What's that?
That is so funny. I did notice all that was gone.
Yeah, right? Seriously.
New hobbies.
Yeah, it was like all missing. I mean, most stuff was missing. It was like paper towels and toilet paper and freaking flour. So here's the thing. Sourdough bread's actually really easy to make. Let's see if I can find an infographic. How to make sourdough bread infographic. Keep this really simple so we don't go on a crazy long tangent here. Yeah, it's pretty freaking simple. Take a little bit of flour, take a little bit of water, add a little bit of yeast, right? Add some sugar in there to feed that yeast. And then you just plop it in a jar with no oxygen, right? Now that yeast is kind of like a bacteria. Okay. And bacteria is like a, we've talked about this before. It's kind of like a little critter, it's like a little, animal. And so what ends up happening is it does whatever and what every other animal does. Like we're potty training a dog right now. I am intimately familiar with this process. Food goes in, poop comes out, right? Like that is exactly what happens. That's what makes sourdough bread actually. The flour, the sugar, and the yeast is the bacteria, right? It all starts to like eat, those carbohydrates, and then it's basically pooping out little bits of CO2. And that's why, like, when you look at sourdough bread, it's got like little air pockets in it. If you look at it, it's got these like little porous holes in it. Those little holes came because like those are little air pockets. I hate to say this, guys, but that's like, that little pocket was made by bacteria farts. Like, that's really the whole process there. So what ends up happening is that is very acidic. It's very tangy tasting, right? And that's why like sourdough bread has a little bit of it doesn't taste quite as sweet as some other types of bread. It's like kind of sour tasting, right? By the way, you have done this process by mistake before. I assume. I'm sure everybody in here has done this once. If you've ever, and Chris, we were just talking about this like a couple nights ago, right? Where you make a protein shake, right? And you shake the whole thing up and you drink it and then you forget about it, right? Like you got the lid on still and you forgot about your protein shake. Maybe it's rolling around the back of your car for a couple days with the lid on. And then you're like, oh crap, I forgot. And then you go in and you take the lid off and that sour, like horrible smell like comes and like hits you in the face, that's kind of how we make sourdough bread. That's how we make yogurt. That's how we make beer, wine, pretty much anything that's fermented. It's where bacteria eats like sugar molecules and stuff like that. And then it's filling the chamber with all of these byproduct gases, right? CO2 and a bunch of other stuff, right? And because it's a non-oxygen environment, eventually all of the oxygen gets eaten up and there's no oxygen left. That's when fermentation really starts to kick in. And that is what's happening in glycolysis. That's what's happening in sourdough bread making and beer and wine and like anything that's fermented, kimchi. I can't think of any more fermented foods, but for some reason this morning. But that's what happens. These pyruvates, that pyruvic acid, eats up all the oxygen. And when there's no oxygen left, they start to ferment. And so fermentation takes place. And that pyruvic acid becomes what we're all very familiar with, lactic acid. Okay. And lactic acid is very acidic. It's in the name. In fact, it's so acidic that it's what's responsible for like sitting on our muscles and creating all that damage. Remember yesterday we talked about the digestive system and I said if you were to take your stomach acid out of your own stomach and pour it on your own arm, you're not immune to that stomach acid. It's so acidic it would dissolve and give you a chemical burn like touching battery acid would, right? That's what hydrochloric acid does. Well, lactic acid, it's definitely not as strong as hydrochloric acid, but it is still very much an acid. It's very acidic. So when it sits on our muscles, that's what creates all this like cellular damage, which results in muscle growth. Your body looks around and it goes, what did you do to all of my proteins? It's like, what have you done? You broke all my actin, you broke all my myosin. And then your body has to like work and go, all right, well, I'm going to repair this, but I'm going to repair it a little bit stronger and more resistant to damage in the future, right? I built my house out of straw and that didn't work. It got, broken down. So now I'm going to build my house out of sticks, right? Guess what? We go to the gym again and we work out even harder. And now that we're working out even harder, we create plenty of lactic acid that damages the old proteins and the new proteins. We make just as much cellular damage as last time. And all that lactic acid, breaks everything down. Your immune system comes back and goes, what happened to my stick house? Right? And then it goes, ah! And it makes it a little bit stronger and a little bit more resistant to damage. And it builds out a brick. And then, we go and we throw another plate on the bar and make it even heavier. And then we work out again and it gets damaged and broken down one more, another time. And then, your immune system comes back and is like, come on, you're just constantly like sort of undoing all of this like anabolic stuff, which is great. I mean, that's how we get stronger, Again, I love that I love that video that we just watched because I love that quote, right? Meaningful growth comes through challenge and stress. By challenging our body, we create enough damage that our body's immune system goes, well, if you're going to keep doing this, I'm going to make the body more resistant to damage in the future so that this freaking place stops getting broken down, And then you got a brick house, then you got a steel house, and then you got like an adamantium house, like, it just gets stronger and stronger and stronger until eventually, like, hopefully you can't break it down anymore, and you're just maintaining a high level of like strength and athleticism and stuff. So that is part of the reason why we really like to train in glycolysis, right? Glycolysis is this really intense energy system that produces a lot of ATP very, very quickly, but lactic acid eventually starts to build up. It starts to sort of overtake things. And there's just a lot of lactic acid in the area. That's where you have to get tired and you kind of have to like slow down. You're like, okay, now I got to kind of like back off, right? So you create pyruvates in glycolysis. Now, what happens to those pyruvates? Like I've been talking about mitochondria a lot, but we haven't really gotten there yet, right? So what's going on with all that lactic acid, right? Why is the mitochondria the real powerhouse of the cell? Like why not glycolysis, right? Like glycolysis spits out energy really rapidly, right? So isn't that like sort of like the best version of energy production? It kind of depends, right? Unfortunately, the problem with glycolysis is you have all these byproducts, and those byproducts leave us exhausted. They start to build up, and eventually they kind of gum up the works. There's just too much acid to keep going. So luckily, years and years and years ago, an animal cell somewhere ended up sort of shimmying up next to like this little like other critter called a mitochondria, and it ate it. But rather than like digesting it, the cell kind of realized like, this thing's really good at spitting out energy. And the mitochondria is like, you know what, this thing produces a lot of lactic acid, which is my favorite type of food. And so we have this kind of symbiotic relationship with our mitochondria. And so what the mitochondria is, we call it the powerhouse of the cell because it spits out a ton of energy using the byproducts. So before we had 1 molecule of glucose, we got 2 molecules of ATP, right? Well, after that, we also had the pyruvates. Those pyruvates ferment into lactic acid and it goes into the mitochondria. So from that initial 1 glucose molecule, right, we got 2 ATP, some lactic acid, and now that lactic acid is being used to produce even more ATP. And this is going to spit out about, depending on who you ask, 32 to 36 molecules of ATP. That's way more than making 2 every time, right? So like our body was like, this is great. I'm going to keep this mitochondria thing around. And that's sort of how it sort of kind of came to be in animal cells and stuff. So mitochondria works a little bit different, right? This is where we start to get aerobic metabolism. Because here's the thing, it can use that pyruvic acid, which has become lactic acid, to produce ATP, but it's not able to do it without the help of oxygen. And that is where we started to develop like really advanced respiratory systems, right? Is because like we needed to bring in even more oxygen to make our mitochondria even better at producing energy. So that's sort of like where we sort of evolved from the energy production standpoint, right? So you can see here, right, that glucose will split into a little bit of ATP. It's going to create, remember I said it actually creates 4 ATP, but it's netting 2. So one of them is going to get used over here to help convert that pyruvic acid into lactic acid. One of them is going to get used over here to convert this pyruvic acid into that lactic acid. You got 2 left over. That's the 2 that we net, and we can use that in our muscles to, do work and stuff, right? Our muscles can use that ATP to contract or do something else, right? Now we are left with a bunch of lactic acid. So guess what? That lactic acid is then going to go into the mitochondria, and a little bit of oxygen is going to come in as well, right? Oxygen is sort of going to join the party here. So the mitochondria is going to take in the byproducts of glycolysis and a little bit of oxygen, and it's going to spit out ATP. Now, I will say the mitochondria, your aerobic energy production, right, is pretty complicated, right? It is pretty darn complicated, actually. So I'm gonna sort of like relabel this here. I'm not relabel. I'm just gonna add like a major title here. So this is the anaerobic energy production. Anaerobic energy production is pretty simple. I mean, it's still gosh darn complex, but anaerobic energy production really only consists of glycolysis. That was it, right? The aerobic stuff happening in the mitochondria is pretty complex. I'm not going to go super in depth into this today because we do it much better in other classes. But let's take a look at aerobic energy production, right? Aerobic, which is going to take place afterwards, is going to be right here. So this is going to consist of a couple different processes. Now, we're only going to see two today. But for those of you who have been through our other metabolism classes, like you'll see we've got two things listed here. You'll remember that aerobic also has aerobic glycolysis, which is glycolysis that actually takes place in the mitochondria. You know, it's the same process, like nothing different is happening there. It's still glycolysis at the end of the day. But aerobic metabolism, the reason it's so complicated is because like this is going to use like byproducts and products. It's going to spit out like a whole bunch of stuff, right? So this is going to be happening in the mitochondria, okay? The first one we are going to see, the first part of this is going to be known as the Krebs cycle, okay? So the Krebs cycle's ingredients are those byproducts I just talked about. They are going to be the pyruvates, or we could call that lactic acid at this point, right? The pyruvic acid, which has fermented into lactic acid, okay? And then what that's going to do, the product here that we're making, we're going to get 2 more molecules of ATP, which is not exactly a ton. So you might be thinking, wait, you just said that, you know, we're creating a lot. Well, we are, but we got 2 processes here. The byproduct, you know, the leftovers, just like last time, the leftovers of glycolysis was pyruvates. The leftovers of aerobic energy, the leftovers of the Krebs cycle are going to be these molecules of NAD and FAD. Okay, NAD and FAD are what we call them. Okay. Now, NAD and FAD are going to go through another process. This is still happening in the mitochondria, but this is where we are going to do what's called the electron transport chain. And now we've got ingredients here, which are going to be NAD. Oh, shoot. I also forgot about the ingredients. Sorry. Pyruvic acid and oxygen. It does take a lot of oxygen in order to get this to happen as well. We've got our pyruvate plus oxygen, right? Lactic acid plus oxygen. Electron transport chain, the ingredients are going to be NAD, FAD, and oxygen. So we also have O2 there. Our product is going to be 34 ATP molecules about. And our byproduct is going to be a little bit of CO2 and a little bit of water, actually, a little bit of H2O. Oh gosh, capital. Sorry, just trying to get this all to fit. So that is the actual very freaking complicated process of aerobic energy production, right? So this happens in the mitochondria, like I said, and we are going to take in that lactic acid and spit out a little bit of ATP in the Krebs cycle, but we create this NAD and FAD stuff, and then we spit out a ton of ATP after that, right? So if we look at aerobic energy production, like I said, it does take place in the mitochondria. And there's a little bit of a different way to look at this, right? Here's sort of the process, right? This is why we get all the ATP that we're talking about. So glucose becomes pyruvates, which becomes lactate, right? Pyruvates ferment into lactic acid. So then we make that pyruvate, that lactic acid. It becomes this other molecule called acetyl-CoA, which kicks off the Krebs cycle. And then that acetyl-CoA's byproducts are the NAD and FAD, which come out to spit out the ATP that we talked about. So 8 plus 6 plus 24. This one they're saying 30. They're saying 38 ATP. Again, we're still studying this stuff. None of us kind of agree. Like if the cell is really efficient, you might get like 38 if it's. But I think the average that people say is like 32 to 34. And these take place in different spots, right? Again, if we look at like where this is coming in a cell, right, is like some of it is happening in the cytosol, in the cytoplasm, right, just outside the mitochondria, is the fluid, right? And then the other part's taking place in the mitochondria. It goes through the Krebs cycle first, and then eventually goes to the electron transport chain, and that's what spits out all of our energy. So very complicated process, right? So a lot of times when we're talking about metabolism, what we're talking about is how we are, or at least when we're talking about metabolism from our perspective, right? Like I said, it's all reactions that are taking place. But like when we're talking about it from like a training perspective, right? We need to make sure that we are producing enough energy and like not producing too many byproducts, or maybe we're producing enough byproducts, right? Like we need to be able to like balance this all out in order to support whatever type of athlete we happen to be. Now, I did say we get a ton of ATP in this aerobic energy production, right? We're getting like 34, 30, plus another 2, like 36, 38, getting lots, right, of ATP there. So we're just creating a ton of these little molecules, which are going to allow us to, again, break those molecules to release lots and lots and lots and lots of energy. The problem is this part here, the aerobic side of things, relies on glycolysis happening first. So this is actually a very slow process. While it creates a lot of ATP, it is slow in how it does it. Whereas this creates a lot of ATP, but it only creates like a little bit at a time, very, 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 very fast. So we can actually start to tie these different types of metabolism, these different energy production types, to intensities and durations while we're in the gym, right? So like if I want to target glycolysis, that's a very fast energy production. Well, what I'm going to do is I'm going to lift pretty intensely. I'm going to use a lot of muscle all at once. That is going to produce a lot of energy very, very quickly. That's glycolysis. That's going to last anywhere from it's going to last about 30 seconds. They say about 20 to 30 seconds. If I'm really good at it, let's say I have let's say I'm let's say I'm like this type of bodybuilder, just like a big freaking, not that synthol guy, but just like, kind of just like a big bodybuilder type, that's a lot of, those are large cells, right? And they have a lot of cellular fluid that is going to be really good at, that glycolysis energy production. The cells are just big and puffy. There's a lot of fluid within them, right? So because of that, I'm pretty good at that style of energy production. Maybe I can even get it to last 60 seconds, but either way, it's a short duration energy production type. It really doesn't last that long. It spits out a ton of energy and then is exhausted, right? It's like a firework rather than like a candle, you know? Candle is going to burn a lot longer. Fireworks going to burn pretty freaking bright, and then it's going to be kind of done, right? So that is the glycolysis approach to things. So as an athlete, if I'm trying to like get better at big bursts of energy, I'm training primarily in glycolysis. I'm going to do short duration sprints. I'm going to lift really heavy for a low to moderate number of repetitions, right? And if I'm targeting more on the aerobic side of things, right, aerobic and respiration, right, this is requiring lots of oxygen. Well, then I'm going to do long duration exercise, right? I'm probably going to go for a low intensity run for a long duration, and I'm going to lift at a low intensity in the gym for a high number of repetitions, and that's going to target my aerobic production. Now, I mentioned, you know, when your body is experiencing growth, it's because like we get damage and then our body repairs that damage, but it doesn't just repair it back to where it was, it repairs it a little bit better. And that's how we get a little bit bigger, a little bit bigger, a little bit stronger, a little bit stronger, right? But we have to create like that damage in order for that to actually happen. Well, now let's take a look at like, oh, well, if I created that damage by, again, sprinting over a short duration, what type of like athlete is that going to grow? Well, it's going to grow the type of athlete that works really hard for a short amount of time, you know, sprinting or something like that. It's going to target glycolysis, and it's also going to target the type of growth that corresponds with glycolysis. So it will make larger cells that are very puffy, right? It has a lot of cytoplasm to be better at glycolysis. And if I do a lot of long duration, you know, running, my body's going to go, oh, we need more mitochondria. And so it'll make more mitochondria, it will make more enzymes that'll carry oxygen more efficiently, make more capillaries, right? We're going to get different types of like adaptation to whatever type of metabolism we primarily train in. And that's really the key concept of why we're even talking about this stuff, because you're going to have athletes that need to run for long durations. Great. Don't train them in glycolysis, train them in running long durations, train their aerobic energy production, right? You're also going to have athletes that need to be able to, you know, make a breakaway faster than another athlete. So they need to do like a big sprint and they need to be the faster of the two. Great, train them in glycolysis, right? Or maybe you have a power lifter. We didn't talk about this today, but you know, they'll use the ATP-PC system, which is actually a precursor to all of this. We'll talk about that in other classes. But it does tie directly. Like sometimes the metabolism stuff, it's easy to get lost in the weeds and be like, all right, like this is all really complicated and I can't see any of it. So how the heck do I like, you know, use this information? But it is tied directly to our gym, right? We talked about this when we were at Sochi and we were talking about the different types of cellular growth, right? You can either make more rods, that'll make the cell bigger. You can make more fluid, that'll make the cell bigger. Or you can shove some extra mitochondria in there and it will make the cell bigger, but not by much, right? And that's the difference between like anaerobic growth and aerobic growth. Whew. Any questions? Surely we've got some, you know, questions, comments, concerns. How does everybody feel about that? Does that make sense for the most part?
I just have a quick question.
Yeah.
What about wait. Okay. If somebody take it, you know, all this product to say they will increase your energy level, they will increase your metabolism activity. So what
is that stuff? What is that stuff?
I mean, what is how the body act when somebody take that product? I mean,
yeah. So there's a few products out there that are all claiming to kind of do that, right? One of them is like, you know, like an energy drink, right? Is that the one you're thinking of? You think of energy? Are you thinking of
any energy drink, pills, you know, like for example, the fat burner.
Oh, like hydroxycut?
Yeah,
stuff like that. Okay. Yeah, so yeah, those things are supposed to increase your metabolic rate, right? But here's the thing. Unless you are taking like what's called a synthoid, which is like a medicine for metabolism. I'm sorry, for metabolism. It is actually a medicine for your thyroid to speed your thyroid. Unless you're taking something like that, like thyroid hormone does speed up your cells process. It makes them run a little bit faster. But also will totally screw you up metabolically because now you're just flooding your system to make everything run fast. Whereas like we really don't want everything to run fast. We want certain things to run fast while we're doing certain things. We want other things to run slow while we're doing certain things, you know, like, and that's where you can see like some people who do create too much, they do create too much like thyroid, they'll get what's called Graves' disease. And Graves' disease, you'll notice they look like this. They look kind of bug-eyed, actually. And the reason they look like that is because like the muscles of their eyes are actually just constantly, they're kind of bulging and swelling because like those muscles are just contracting, even though they should be relaxing. So not a great choice to take extra, you know, thyroid medicine, right? And it does all kinds of other things too. It causes like swelling, and you can see here that's the thyroid is just causing like massive amounts of growth and fluid buildup and stuff like that. So that's what like Graves' disease is, right? So luckily for everyone, that is not what energy drinks are. Or like fat burners. That's not what they do. So when fat burners say that they increase your metabolism, let's take a look at like a fat burner, right? I'm gonna do this on incognito because I don't want ads. Let's see here. There's a lot of them out there, right? If you look at what their ingredients are, let's see. Yeah, I'm just gonna click this one. Oh yeah, Amazon's got the ingredients listed, I think. Where's my ingredients list? Pictures, there we go. Okay, so first off, it's got vitamin D in it, right? Vitamin D doesn't necessarily increase your metabolism, so that doesn't have anything to do with what they're claiming here, right? Next thing they got a proprietary nighttime fat burn blend. Okay, what the heck does that mean? White kidney bean extracts, I don't know what that is, right? Green coffee bean extract. Okay, so basically we're extracting some caffeine, right? We see L-theanine, L-tryptophan. Those are both amino acids. So amino acids do sometimes like produce a little bit of energy. Valerian root extract, we don't know what that is. Lemon balm extract, we don't really know what that is. So it's a lot of like flowers and stuff. And then there's a little bit of melatonin in there to help you like stay asleep, right? So when I look at a fat burner like this and I look at those ingredients, you know, it's like, all right, that's honestly not really doing much. It's a lot of like, you know, leaves and plants and things like that that someone saw, like they probably gave someone those leaves and plants at one point, and then that person lost weight during that time, and they're like, oh, we must have boosted their metabolism. And it's like, no, they probably just like maybe had a different lifestyle for a little while. And this is where like a lot of supplement claims really are unfounded, right? Now, it's not saying that like some fat burners don't work. Let's take a look at like, honestly, like hydroxycut, which is sort of one of the more famous ones. You know what? I'm just going to go back to Amazon because that worked pretty well. So here's hydroxycut. This is probably the most famous fat burner on the market. Now, why does this work? Well, let's take a look at the ingredients here. You know, I said it's so famous. Why is it so famous? Zooming in like crazy because that's very small. You take a look at the ingredients. Green coffee extract again. So now we've got two fat burners that we've seen that have caffeine in them, right? Coleus extract. I don't actually know what that is. L-theanine again, right? So again, a little bit of an amino acid to help with energy production. Cocoa extract, which coffee, by the way, does have even more caffeine in it. That's one of the reasons why dogs can't have chocolate, is because their heart sprays too fast and it can be really dangerous. So we see caffeine again. Yohimbe extract, which is from like a plant like yohimbe bark. which also is like a stimulant, right? So like that one sort of like makes you run a little bit, you know, like stimulates your energy production and kind of just makes you a little bouncy. It's kind of like caffeine. So now we're really seeing kind of a through line here with like caffeine and stimulants. So when a fat burner on the market says that it actually stimulates like, you know, to speed up your metabolism, what they really mean that they're saying is that you will have a lot of caffeine running through your body and you're going to be a little bouncy all day. And so by being a little bouncy all day, you know what that does? It burns calories, right? If you start bouncing your leg, you just find that you're pretty irritable. Your heart is racing a little bit faster. That's burning a little bit more energy than it would have. That is how fat burners work. They don't actually increase your metabolism. They increase you. Does that make sense?
Yeah.
Yeah. So fat burners basically just make you a little antsy all day. But you don't necessarily need them to get those benefits. You know what you know what works just as well as like a fat burner? Put an alarm on your phone every hour on the hour. Every time it goes up, every time it goes off, get up and go walk, do a lap around your house, do a lap around the office, come back and sit back down. You will burn extra calories throughout the day by doing that. Start taking the stairs. Start parking as far away in a grocery lot as you can. David, do you have a question? I saw you unmute there.
Oh, no, I didn't have a question. I just wanted to like chime in. So essentially our body, right, when it produces like ATP cells, does all of the cellular respiration. It does that because our body, we place a lot of stress on our body, right? And it's just reacting to okay, I had a brain fart there. It's pretty much reacting to the demand, right? It's like demand and supply, right?
Absolutely, right? You can't do anything without the energy necessary to run your cell. You get that energy from ATP molecules.
Right. And you said that, so depending on, like, let's say we have a specific client, right? Like, I have a sprinter. I would want to train them in glycolysis, right? Instead of training them to be like you said it before, you need to do it in specificity, right? Like you can't be like, oh, let me just train this dude to run a marathon. He's not training to run a marathon.
Exactly. So it doesn't make any sense. Yeah.
Right.
Let's take a baseball player and teach him how to be a better, teach a baseball player how to dunk a basketball. Why? Those have nothing to do with one another, right?
Right.
Same thing is true when training like your energy systems, for sure. If you're trying to like, be like an NFL player, like let's say you're being like an offensive lineman, right? That's a big, heavy strength situation. It doesn't make any sense for you to go to the gym and try to do, it's like, what I want to do? I want to work up to 200 push-ups consecutively. Cool goal. I think that's fun, but it doesn't have anything to do with that sport. So why do it? One's aerobic, one's anaerobic. Yeah.
So it's just like, you really just got to look at it for what it is and then be like, I got to do this instead of this.
And it comes down to the biology, right? We know all of what I'm saying right now is true because of the way our cells produce this energy, which is why we're studying it, by the way. It's the why behind, when you see like a workout, right? You always see these, you guys, I'm sure you've seen these infographics on like Instagram. Types of strength. I don't know if I'll be able to pull this up because I have no idea how to Google this. Rep ranges infographic. Yeah, kind of that. Yeah, there we go. You always see this kind of stuff, right? I see this. There we go. This is what we're looking for. There's another really good one there in the middle. They always show you these like pictures of like one athlete versus another. I get these on my Instagram all the time where it's like, what's the difference? If you're going for strength, 1 to 5 reps. If you're going for size, go 6 to 12, right? And then it's like they show like pictures of what people look like, right? Low volume is decent gains and more volume is more gains. And then like, but too much volume, there's just so many of these infographics, right? 10 to 12 is poor for strength, 6 to 8 is good for strength, 4 to 6 is great for strength, right? Why do we believe something like this? Well, why is there so much information out there like this? Well, again, it's because they are like, they're looking at the physiology, they look at the cells, right? these all get you like 1 to 5 reps builds you strength, 6 to 12 builds you size, 12 to 20 builds you endurance. They all build muscle, but this is for endurance, this is for size, and this is for getting stronger. Why? Again, look at the cells, right? We know how they respond to that stress.
Okay.
So Danny, I do got one more piece of info to finish answering your question. So you also see stuff like energy drinks, right? So fat burners, oftentimes they actually don't increase your metabolism. They just increase like what you do throughout the day, right? But what about energy drinks? Do energy drinks, because I've definitely had an energy drink and I'm like, I feel great, right? Or what about caffeine? It's like, I feel awake, right? Well, I didn't go super in depth into it today because I don't want to scare anybody away. But we look at the Krebs cycle. This is actually what's happening in the Krebs cycle. It actually looks like this. It is very complex. There's that pyruvate, which has become lactic acid, which becomes acetyl-CoA, which then starts the Krebs cycle. And so you get citrate and acinitate. Oh my God, I can't say any of this stuff. You see all these like friggin' things here, right? And it's spitting out all this stuff, right? These little molecules that's spitting out. That is the NAD and the FAD. Where's my FAD? Or NADH, I guess. That's your NAD and FAD getting spit out, along with, and you can see, where's my ATP? Where are we creating it? Well, there's a little bit of ATP and a phosphate, so that would be ATP in the end. Good Lord, citric acid cycle. So NAD and FAD getting created there. And there's a little bit of ATP coming out, right? And there's a little bit of ADP and it gets resynthesized into ATP. So the Krebs cycle over here is very, very complicated in itself. It spits a little bit of energy, it spits out a little bit of byproduct there, right? But what actually makes all of those little bits happen, right? Each of those little things that we saw, all those really big, complicated like names and words and stuff, those are actually your B vitamins. So like when you see an energy drink, you will notice like what it has in it is a lot of caffeine, which, you know, is a stimulant that does speed you up. So hydroxycut and energy drinks are very similar to one another. But what you'll see in an energy drink that you won't see and then there's also C4 that has like creatine in it, which also enhances performance for its own reasons. Is it Starbucks? Starbucks has its own energy drink now? Good Lord. So like you'll see all these things. I'm looking for one where it actually says on the front where it's like, it's packed full of B vitamins. But if you look at the nutrition facts panel here, you will see a whole bunch of vitamin riboflavin, which is B5, I think, niacin, which is B3, B6, and B12. You are seeing this thing being loaded up with sugar, which helps with glycolysis. It's going to be loaded up with B vitamins, which helps with the Krebs cycle, and it's probably got a lot of caffeine in it to help with just like giving you a little bit of energy in the moment. So there's not a lot of difference between thermogenic fat burners and energy drinks, but the way that they both work by increasing your metabolism is by speeding you up or making it easy for your body to actually do metabolism. Now, do I think you should be getting those B vitamins from energy drinks? Definitely not. We try to, you know, I think you're going to be much better off getting them from like food products. And honestly, like food products that are packed full of B vitamins are usually like protein based. So like, this is why like, you know, sometimes you do feel like you get a little bit of energy from just a carbohydrate by itself. But when you pair that carbohydrate with a little bit of protein, you feel like you're getting a lot more energy. That's because of the B vitamins. So that's what those various products are out there on the market, and that's sort of how they work. Does that make sense, everybody?
Yep. Thank you.
Yeah.
Cool. Not saying they don't work, by the way. I mean, honestly, they do have some type of effect. But unfortunately, they come with side effects. Like, you know, And then there's other ones too, really quickly, just to address what's the other, like pre-workout, right? Pre-workout's always sold. You'll notice it's basically a very similar. I did this on a regular tab. I'm gonna get pre-workout tabs. Oh no, I just entered Ad City population me. You'll notice pre-workout is a whole bunch of B vitamins, so B6, B12. It's got some calcium in there. Calcium, actually, we do know is responsible for muscle contractions. So if you're using this as like a workout thing, kind of nice to have some extra calcium in there just in case. Magnesium can act as an electrolyte. Sodium is definitely an electrolyte. Potassium. So now you're like looking at this pre-workout supplement and you're like, oh, okay. So it's basically like an energy drink with like Gatorade in it, right? Like Gatorade is sodium and potassium. It's electrolytes, right? So energy production that way. Cool. Then you look at the performance blend here, and it's got creatine monohydrate, beta alanine, arginine, right? And things like that. That is going to be a couple of your branch chain amino acids. So those are your BCAAs plus creatine. And creatine does help with energy production. I'm not talking too much about creatine today, but creatine is actually something that predates glycolysis. So like glycolysis, I said, was about 30 seconds. Well, the first 10 seconds actually relies on creatine. Your body can make creatine, but you can also take it, you can sort of flood your system with it. So getting creatine in here can increase performance if you're in the 1 to 5 repetition range. And then you can see the energy blend, taurine, caffeine, right? Again, there's all the caffeine stuff. So pre-workout is very similar, right? It's just pre-workout is like taking hydroxycut plus an energy drink plus a Gatorade. And plus creatine. So that's really what all these supplements kind of are. But again, these are all things that I've been describing. Like you get them from food, you get them from getting a good night's rest, right? So do I take pre-workout? No, I'll take creatine, when I'm on like a strength phase. Yeah, absolutely. I'll take creatine. There's really no downside. Creatine is one of the very few supplements that I will absolutely put my name behind. It has been proven in pretty much every circle to be very safe and relatively effective, unless you're a non-responder, which is pretty rare, really, really rare. And then there's whey protein. Whey protein is a supplement that I'm a fan of because it's literally just getting protein in a very easy method. And it's highly, highly digestible, so it gets absorbed really easily. And then the other one that I am a big fan of when it comes to supplementation is regular old caffeine. I'm not saying that these energy drinks don't work. Caffeine does give you more energy, which can increase your athleticism during events. But we need to be aware that all of these come with side effects. Creatine unfortunately leads to like water retention, which is a very minor side effect. If you go into the beach, you don't want to retain some water, stop taking creatine for a couple days beforehand, and then that's it. Whey protein actually, I guess, doesn't have any side effects, although it's not a very nutrient-rich food. So if it's taking up space in your diet, that could be a side effect. And then caffeine does have some side effects. It does cause like increases in blood pressure and increases in heart rate and stuff, which can be fine. But if you have like heart problems, you should be cautious of. Okay, we ended up on the supplement train, but hopefully that helps us understand like sort of how this whole thing works, right? So again, when we're talking about like what our metabolic rate is, we're talking about how many calories we're burning each day. Releasing calories, we get that energy from food. Like a calorie is a ton of ATP, right? Remember, ATP is incredibly, incredibly small. Like, let's see if we can talk about this. Yeah, there's about 7.3 calories per mole of ATP, which a mole, that's a very complicated measuring tool, but it's a lot. It's a lot. So you're actually creating trillions of ATP molecules constantly. So it's a very high energy molecule. we describe it in terms of calories because it's a way easier form for us to kind of look at. So when we're talking about how many calories are in something, talking about how much energy is in something, it is describing how much ATP is going to be released there. So there's a lot of energy trapped between the bonds of that ATP molecule. We're going to split off that bond. So we need to get plenty of food in for us to be able to create that energy because food has calories in it. If we're talking about using nutrients for energy, our favorite source of energy is going to be glucose. Glucose is your body's favorite ingredient. Now, that's not to say that it's the only ingredient. You know, we did sort of look at this. We looked at like glycolysis, the ingredient was glucose here. Well, what if you don't have any glucose? What if you, for the last 24 hours, have not eaten any carbohydrates at all? The only thing you've eaten is pure isolated protein somehow. Like you also didn't get any fat. I don't know how you did this, but somehow you got pure protein in your diet and nothing else. Well, you know what your body can do? Your body can take that amino acid that is found within that protein, break it down, and guess what? Now it's got a molecule of glucose, and it goes through glycolysis. Cool. Your body got its favorite fuel source, even if you didn't want it to. What about fat? Yep, same thing. Your body can take fat, turn it into glucose, and then use it to produce energy. So our body's favorite source is just to go straight to the source, which is glucose, right? Our body's favorite sort of way to produce energy is glucose because it's fast, right? Now, other bits of it can come from glycerol, you know, that you're going to get from fat. Some of it's going to be from fatty acids. You're going to get that from fat, and some of it can be amino acids. But those are all sort of roundabout ways of doing this, right? With the fatty acids, you've got to oxidize them first. With the protein, you got to rip the nitrogen skeleton out. And by the way, like that nitrogen skeleton is going to leave a byproduct. Now there's extra nitrogen floating around in your body that your body has to process and get rid of in your waste, right? So you're going to have increased urea production. You're going to pee more often, and you're, you know, probably going to lose some urea in your sweat and stuff too, which means you're not going to smell super great. The byproduct of fat, right? Those are going to be ketone bodies, right? And if you flood your system with those, that can actually raise your pH levels. So you need to make sure that you're balancing that out with plenty of like alkaline food so that you don't become hyperacidic. Because then you can start suffering from what's called hyperacidosis, and then your body stops working. You know, like, you know, there's definitely some byproduct. Again, our body's favorite is going to be glucose. This is why, again, carbohydrates are not bad for you, even though sugar has been shown to have some negative effects. Sugar is not great. Carbs are awesome. So your metabolic rate. Let's go ahead and talk about the general viewpoint. We've been getting really complicated about metabolism, right? Let's zoom out and let's have a conversation with our client, a little bit simpler, right? Well, your metabolism is how your body is using all of these materials, right? Some of it is not even like energy producing materials. Some of it's just like, you know, minerals, right? Or vitamins. Vitamins don't have any energy of their own, right? They don't have any calories in them, but those B vitamins are going to help with the Krebs cycle. So they do give us energy in a sort of roundabout way. So you'll also see minerals here, and minerals are really important for other parts of your metabolism, like giving your body structure or fluid balance, which I just talked about, like helping with the pH and stuff. They create muscle contractions, right? Sodium and potassium, that's how we created those electric signals that we use in our nervous system. So without sodium and potassium in your diet, your body can't do that. You can't have like a nerve impulse, you know? So we really like vitamins. They definitely need to be part of our diet. They are chemicals that are basically inorganic. They don't have any carbon in them. So they're not part of carbohydrates. They're not part of protein. They're not part of fat. They're their own little metals that we use for other various reasons. Vitamins are also very complex substances. There's going to be two major categories of vitamins here, right? You're going to have your water-soluble vitamins. Those are the ones that are transported and then they dissolve in water. So the way your body uses them, use a little bit of water to kind of break them up and release their energy. So which ones are water-soluble? It's your entire B complex. So those energy drinks, that hydroxy cut, that pre-workout, all of those had a bunch of B vitamins in them. Again, the B vitamins are what go through the Krebs cycle to allow it to happen. They're all those big, you know, that's what those B vitamins actually are. They're all these little enzyme thingies, right? So those are all like, B vitamins that are allowing that to kind of take place. And then vitamin C, which is used for other reasons, right? Those are all those are all of the water soluble vitamins. So C and all of the Bs. And then you got fat soluble vitamins. Fat soluble vitamins are amazing, right? Those are vitamins A, D, E, and K. They dissolve in fat. So you actually need to have fat in your diet to allow those to kind of break up. And they are transported in fat as well. So they get carried around thanks to fat. These usually assist in the utilization of those minerals we talked about earlier. So like when your body needs to use calcium, for instance, it'll help do that thanks to vitamin D. It also aids in physiologic processes, right? Your blood clotting, for instance, we need vitamin K to be able to do that. And some of them even act as antioxidants, which are going to help stabilize and fight different types of cancers. So we're a huge fan of vitamins for that. So that is sort of what we're looking at in a general metabolism thing. How do we want to ensure that we are fueling our metabolism effectively, safely, and in such a way that's going to help lead to a long, healthy life? Well, we are going to ensure that we are getting a very balanced, nutritious diet. Plenty of carbohydrates for the energy production, plenty of fat for hormone and also energy production, and plenty of protein to make sure that we're repairing body tissues. Now, do not write these down here on the PowerPoint on the left. These are the Memler's guide to macro. We want 45 to 65% carbs is our recommended. We want 20 to 30% fat and 15 to 35% protein, or no, 20 to 35% protein. Don't pay attention to these numbers. Pay attention to the numbers that are in your NASM textbook. But we talked a little bit about this yesterday, right? We looked at our nutritional guidelines yesterday, right? We've got monosaccharides. Those are simple sugars. That's glucose, right? That can go straight in for metabolism. We got complex carbs, which are lots of glucose all tied together. So that's great, like starches and, fibers and things like that. Ideally, when it comes to maintaining a healthy metabolism, we want to have complex, naturally occurring carbohydrates rather than simple, sort of processed carbohydrates, because that is going to keep our blood sugar levels from overly spiking. If we spike our blood sugar levels, we're just pouring sugar into our blood. Our cells can't do all this other metabolism stuff. You're gumming up the works, So we're going to pay attention to how simple our carbohydrates are. We've also got fats, right? There are saturated and unsaturated fats. The saturated stuff is typically associated with those bad cholesterol. So we call those our bad fats, although they are fine. As long as they're about 10% or less of your diet every day, you're going to be in a pretty good spot. And then we got our unsaturated fats. Those are coming from plants, right? Those are the liquid ones. Olive oil, often from plants. I say fish is actually a great source of unsaturated fat as well. And here's what that kind of looks like. When I say it's saturated, you think of it as like a table. All the seats of the table are filled. So it makes these big straight lines. That's why it can be a solid, because it can stack really efficiently. This unsaturated fat, it's got a couple seats available at the table that form these little kinks. And those kinks mean that it won't be able to stack quite as efficiently. That's why it is liquid at room temperature. We've also got proteins. Proteins are going to generally come from animal sources most often in most average American diets. And that is because they're complete proteins. They've got every amino acid available. Vegetable sources are a great source of protein. Grains are a really great source of protein, but they are incomplete. They're missing 1 or 2 amino acids. So you do need to make sure that you are eating your amino acids in such a way that you sort of pair them up, right? So if you look at a legume, like a bean, right, it doesn't have methionine or tryptophan. And if you look at a grain, it doesn't have isoleucine or lysine. So if you eat a little bit of beans on toast, like a grain, right, now you're getting all 4 amino acids. That's the most British meal ever, by the way. Beans on toast. Now, when it comes to vitamins and minerals, we do want to make sure that we are getting plenty of them. But should you take them as a supplement? I don't know. I don't think it can hurt you too much. I'll take a multivitamin here and there whenever I actually remember to do it. I don't make it a priority. You should never be using vitamins to supplements to replace food, but they can be fine as long as you're not getting them in like super high toxic levels. So they're somewhat controversial, but for the most part, they're fine. Our ideal way of getting plenty of vitamins and minerals in our diet, guys, is going to be through what's called our My Plate. So if your plate looks like this, half of your plate is fruits and vegetables, a quarter of it is like a healthy grain, and a quarter of it is like a healthy lean protein with a little bit of, now this is like dairy. I don't think you necessarily need dairy. You can get plenty of it from here. That's going to be a really good spot, right? If your meals look something kind of like this, healthy grains such as like, whole wheat pasta or whole wheat bread or, whole oats, right? Stuff like that. It's going to be a really good source of complex carbohydrates. Whereas like proteins, yeah, you can get them from eggs or meat products. You can get them from beans even, right? And then the other half is like, vitamin and mineral rich foods like fruits and vegetables, right? See the same thing here, right? This is a really good source of like a healthy freaking plate, Again, I don't necessarily think you need the milk. That's kind of a USDA thing. But milk is a good source of protein. But yeah, all kinds of really good. And by the way, I actually don't think you necessarily need to do fruits and vegetables at every meal. What I often do is like a big serving of fruit for breakfast and then like veggies for lunch and dinner. I think it's weird to eat. Personally, I think it's a little odd to eat like fruits and veggies at the same. Like I would never have like, what is that, like chicken, rice, and then like Brussels sprouts and strawberries. Like that's such a weird combo to me. Love Brussels sprouts though. Like let's go, like, but yeah, so there's a lot of different examples of like, if you can make your plates look like this, I promise you're going to get plenty of vitamins, you're going to get plenty of minerals, you're going to get lots of complex carbs, good sources of protein, and you're probably not going to need to take any supplements. Now, alcohol is on the list here, although it is not considered a nutrient. In fact, it kind of screws up your metabolism. Your body can metabolize it, but at the cost of like slowing things down. Your body will always prioritize breaking alcohol down as quickly as possible. So it slows the rest of your metabolism down, which means you're not absorbing nutrients effectively. And it does have other, plenty of negative effects. It makes your liver and kidneys work really hard, has a lot of side effects. So there are obviously disorders related to nutrition, which is what we're spending a ton of our time talking about, right? We're looking at being overweight and obese. Obviously, the reasons for this are going to be way more complex than boiling it down to a couple simple sentences. But a lot of times it has to do with like consuming too much energy and then not being active enough, right? We're creating a caloric surplus, right? And that does have negative effects. It shortens our lifespan because it's tied to a lot of what we call comorbidities, right? Being underweight, just as if not more dangerous. And this is also going to have like very negative side effects, right? Low reserves of energy, way less like fat available on the body, which means like your body will have a really hard time producing hormones, which can lead to like reproductive disturbances and other like nutritional deficiencies. Last little bit here, I'm just going to kind of blast through this really quick. Part of your metabolism that you can sort of observe externally, like if you're looking at things, is like your body temperature. So whenever your body breaks a molecule of ATP, right, we talked about how it kind of goes, kicks that off and then releases a bunch of energy, right? Well, most of that energy gets trapped by your body and used to power a cell, but some of it gets just kind of released. Some of it just kind of like works its way out, doesn't get captured by the cell perfectly, and just becomes sort of like ambient energy in the form of, weirdly enough, light. Not that you can tell, looking at yourself, but you are actually, spitting off a little bit of light, kind of like a firefly or a lightning bug or whatever you want to call them. But most of it is just coming off as ambient heat. And this is why, like when you exercise, your body temperature actually climbs. Part of that is your blood vessels opening up and pumping blood around, which, you know, is going to carry heat around, so you feel hot everywhere. But the reason that heat is being produced is literally a byproduct of ATP usage, right? So there's a couple different things that are going to affect your heat, like your exercise level, your hormone production. If your thyroid is running really fast and your cells are just releasing energy really quickly, that will also increase hormone production, which is where people who have Graves' disease, they're like constantly just sweating and hot. You know, they're really just hot. Your food intake can actually do that. You know, if you bring in plenty of food, that can actually produce heat. And then age, you know, we tend to be pretty good at producing heat when we're younger, and then we kind of lose that ability as we get older. So there's a lot of different ways that you're going to lose heat. Some of it is through like radiation. Some of it is just passively leaving you. Some of it's through convection, where, you know, if you're getting hit with air, it's actually carrying heat. It's picking up heat and carrying it away from you. There's evaporation, which is where like water is basically carrying heat away from you as it dissolves back into the atmosphere. And then some of it's like conduction. If something has a severe lack of heat, it will absorb it from you. That's where like an ice pack is like, well, I'm very cold. And so it's just taking passive energy from you. Like I said, we don't have to worry too much about any of that. But your body does have a lot of really cool mechanisms for regulating temperature. If you start getting really cold, for instance, your body will constrict blood vessels so it stops losing heat. If you start getting really hot, it'll actually dilate blood vessels in order to vent heat a little more effectively. Now, kids, and this is something we're going to talk a lot about at the end of this module, are terrible at regulating body temperature. They have a lot of surface area and very little blood. So they have a reduced ability to produce heat, and they also lose heat more easily because of all the surface area of their skin compared with their little tiny bodies. Guess what? They're also really prone to overheating because if they do get really hot, they cannot vent it very effectively. So age factors definitely play a role here. Ideally, we want our temperature to be somewhere between like 97.8 and 100.8. Anything above that, I mean, honestly, getting around to 100 is actually like, you're starting to get into like fever territory, at least if it's here. Certain parts of you can be plenty hot, you know. But it's going to vary in parts of the day. It's going to vary by your body parts and stuff. If you have a fever, that's usually a sign that your body is trying to cook some type of virus so that it will stop functioning, because you operate at a very narrow range of temperatures, but so do viruses. And your body knows that. So if it has a virus, it'll try to basically cook that virus by turning off the regulators for your temperature, and you start to develop like a fever, and that can sometimes kill that virus, which is great. Unfortunately, can also sometimes kill you, which is not so great. So your body's kind of taking a gamble there. And then if you are excessively hot, that can lead to like muscle cramping and heat exhaustion, heat stroke. All those things are really dangerous. If you ever notice something like that in your client, try to get them hydrated and stop any physical activity. If they start cramping and stuff, that could be due to excessive heat. Excessive cold is really dangerous as well. Probably not going to deal with that, but that can sort of like damage different tissues of the body. So the body temperature stuff is definitely part of metabolism. It's not really the area that we spend our time talking about. We are more looking at like energy production for us to understand how to effectively apply stress in the gym. Because again, my favorite quote, we're going to experience growth due to challenge and stress. We're trying to get our body to adapt to things. And that's about it. Any questions, guys? How y'all feeling?
Good.
Feeling good. Feeling good. You said this is chapter 20 in the Memlers, right?
19, 20? Yes, chapter 20.
Okay, cool.
And then we'll pair it up with the NASM approach to metabolism tomorrow. So we'll look at that, and that'll be, you know, a little bit different. Tomorrow night, I should say. I will be on a plane tomorrow, but tomorrow night we can definitely follow that up. If you can't make it, by the way, that's totally okay. Just let me know. Like if you got to work or something, you can't make the evening lecture, that is absolutely fine, guys. We will have like the video. There is still a video up for tomorrow's lesson already. and we can have you watch that. And if you guys ever need any like tutoring or stuff, please feel free to reach out.
Okay. I've been reading the memoirs, just reading like random chapters. This book is crazy.
It's fun, right?
It's a straight up like biology book, honestly.
Oh yeah, it's a pre-med book. Yeah.
Yeah, that makes more sense. Cause I looked at it, I'm like, I'm glad I have this book, but why?
Yeah, it's way more complex than it needs to be. That's why we literally only steal. I think we use 6 chapters of it. And we don't use the rest of it.
Yeah, I noticed that because it goes into like the real the nooks and crannies of everything. It's really interesting.
And that's the thing, you don't need all those nooks and crannies, which is why NASM only teaches the basics.
Yeah.
But it's one of those things where like if you get exposed to them once, it makes all the other stuff make way more sense.
Yeah.
Way more absorbable, Like you guys don't need to know how many molecules of ATP are created. But like when it's like 36 versus 2, you're like, oh, that's a big difference,
Yeah, it puts things into perspective for sure.
Yeah. Well, all right.